Welcome everybody. This is Calculus course, 14th week. Now we have a new subject, of course, about dealing with derivatives. Derivative of a composite function. Let's use an example for this one. The function y is equal to 3 over 2x. That is, we have 1 over 2 multiplied by 3x. We can use also like that. Is the composite of the functions. It's easily seen that 1 over 2 u, that is y is equal to 1 over 2 u, and u is equal to 3x. Yeah, this is easily seen that. Here we have you see dy over dx, that is y, derivative of y with respect to x is 3 over 2. We can see this easily from here. And dy over du, derivative of y with respect to u, you can see here that it is 1 over 2. And du over dx, that is derivative of u with respect to x, also you can see the result of this one is 3. And finally 3 over 2, that is dy over dx is equal to dy over du multiplied by du over dx. And you can see that dy over du is here 1 over 2 and multiplied by du over dx, it is 3. It is again 3 over 2. So the chain rule or derivative of composite function is easily can be seen, can be found by here. Yeah. And now another example. Let's give another example for this one. Y is equal to 9x to the power 4 and plus 6x squared plus 1. We know that this one 3x squared and 1 and 1. We know that here 3x squared plus 1 squared. Yeah, it's easily seen. Is the composite of u square, here u square, and it's seen that u is equal to 3x squared plus 1. So dy over dx, also we can find dy over dx by taking the derivative with respect to x. It is 9 multiplied by 4x cubed and 6 multiplied by 2x, and 1, of course, derivative of 1 is 0. We can do like that, but now we are trying to use composite functions derivatives. So dy over dx, dy over du, and multiplied by du over dx. This is the answer. Dy over du is 2u multiplied by du over dx. Here it is 6x. Yeah, 6x. And we know that u is equal to here 3x squared. Let's write it, 3x squared plus 1 multiplied by 6x, and 12x multiplied by 3x squared plus 1. Yeah, this is the result. And if we multiply also to see the final result, it is 36x cubed plus 12x. Also, we can find this one by taking the derivative of this one by x. It is 9 for x cubed plus 6 2x and 0, 36x cubed plus 12x. It can be easy by using composite functions sometimes, but first of course, you think by taking the derivative of original function. Now, we have a theorem for this one. Composite function is like that, f of g and derivative of x with respect to x. So we are trying to find it by like that and multiply by g prime x. So if we have y as fu and u is equal to gx, so we write it as the previous one, dy over dx is equal to dy over du multiplied by du over dx. This is the same as I said in the previous question. Now d over dx, the question is like that, 5x cubed x to the 4 to the power 7. And to find it, first of all, we have to find the derivative of first part, the parentheses. So 7, 5x cubed minus x to the 4 to the power 6. Now I take the derivative of the parentheses, and then I have to find, then multiply, of course. I have to find the inside of the parentheses. So it is like that. So finally, we write that 5x cubed minus x to the 4 6, and this one, if we take the derivative of this one, 5 3x squared plus minus x cubed, yeah, like that. So finally we write that to the power 6, and here is 15x squared minus 4x cubed. This is the result. Yeah. You may write another question dealing with this one. D over dx. Now here's a quotient. We have quotient 1. We can write it like that also, d over dx, 3x minus 2 to the power minus 1. And if we want to think this one as the previous question, we write minus 1, first parenthesis, as I said before. And here is minus 1 is minus 2, and derivative of the inside of the parenthesis. So it is minus 1 over 3x minus 2 to the power 2, and derivative of 3x minus 2, that is 3. And finally, minus 3 over 3x minus 2 squared. This is the result of the question. Now I'm going to write about some more about implicit functions. Yeah. Let's say we have zxy is equal to f of xy we can find delta z over delta x or delta z over delta y by taking the derivative of f with respect to x and with respect to y. We can easily find these things implicitly. Now, what I mean, let's give an example for this one. Let's say z xy is equal to 4x cubed y squared and 4x plus 5y minus 6. And to find the derivative of z with respect to x, we only think the x's and we think the other things such as numbers 4, 5, whatever, and the other variables y's on constant variable as a constant, like for here, such as if you want to take the derivative of x here, we take 4 constant and y square constant. And also, if we take the derivative of x here, we take 4 constant. And if we want to take the derivative of here of x with respect to x, we take 5 and y constant. So derivative of 5y with respect to x is 0, will be 0. Okay, let's see it. Let's see these things. Okay, and now I'm going to take the derivative of the first part here with respect to x. So 4 3x squared y squared plus, now second part it's 4, and third part 5y's derivative with respect to x is 0, and 6 derivative of course constant and 0. So here is 12x squared y squared plus 4. And next one, derivative of z with respect to y is equal to 4 s cubed is constant, so 2y derivative of y, and second part 4x, we are now on the 4x, but with respect to y it is 0 again, and 5y is 5 and 0. So it is 8x cubed y plus 5. Yeah. Now let's give another example for this one. Example minus 7x cubed y 4x squared y cubed minus 4x. And this is the question, and the question asks derivative of z with respect to x and derivative of z with respect to y again. This one. So derivative of z with respect to x is minus 7 3x squared and multiplied by y. Here we put minus 7 and y as a constant, so I put the numbers as as you see, and 4 2x y cubed and 4. Finally, minus 21x squared y 8x y cubed minus 4. This is for x, and derivative of z with respect to y, we can see that again we put minus 7 and x cubed constant, and we take the derivative of y as the first part. So this one is minus 7x cubed, and derivative of y with respect to y is 1, plus for the second part you see 4 and x squared is again as a constant variable, so we put them as a constant. Then derivative of y cubed with respect to y is 3y squared. And finally, as the last part, you can see that there is no y, so minus 4 and x are the constant variables. So we take the derivative of this last part with respect to y, so it is 0. Okay. minus 7x cubed plus 12x squared y squared. Okay, this is the result of the question. Now I have another subject, of course, dealing with implicit functions, but its name is Lagrange function. Lagrange function. We use Lagrange function. Lagrange function. We use this function for finding the optimum values. I mean, for the optimum values is finding the maximums or minimums dealing with the function, of course, such as for the profit function, we use the maximum ones, but for the cost functions, you see the cost function, you saw this is, and for the cost functions, we have to find the minimum of the variables, minimum value for the variables. So for the Lagrange function, we have two parts. We have two parts. For the first part, we have main function. For this one, we use uxy first of all, and minus lambda. Second part is the constraint function. Let's check it. Constraint. I think it's okay, but okay. Constraint is okay. Let's open our time schedule. Okay. This is the constraint function, and this is the Lagrange function. Xy and lambda are the variables, and we write the first part minus lambda, second part. In the second part, we don't use the equality part. I'm going to talk about these things. But for finding the optimum values for x and y, we write delta lambda over delta x, and of course we find the derivative of Lagrange with respect to x, and we put this equality to 0, and we write it as 1. And second, delta Lagrange over delta y is equal to, again, something, but I don't know now, and it is equal to 0, and we put 2 for this one. And finally, we put delta Lagrange over delta lambda. This is the constraint function. Here is the constraint function. So this is the third one. So we use these three equations, and we find optimal x and y. Let's write last thing that I said. This one, we can find optimal x and y by using Lagrange functions. Here, by saying optimal may be maximum or minimum. As I said before, such as for maximum functions, we can use main function. Main function may be profit function, because as a producer we want our profit maximum, and for the main function maybe cost function. So as a producer again, we want our cost minimum. So this may be maximum or minimum as an optimum. Yeah, Lagrange functions used for this one. And now, as an easy question, I have something. So let's write it. Example. Let's say easy question. Easy one. Main function is uxy is equal to xy, and our constraint function is x plus y is equal to 10. Question is find optimal amount of x and y for these functions. Of course, using Lagrange function. Finally, when we found the x and y amounts and put it on the uxa function, we see that our uxa function will be the maximum value. We have the maximum value. Of course, we are going to see this one. Now, first operate Lagrange function. Now xy and lambda. And now main function, x multiplied by y, and minus lambda. This is x plus y minus 10. As I said before, we don't use the equality here, is equal to 10, and we take the 10 here like that, is equal to 10, but we write it like that, x plus y minus 10, and we don't use this equality, and we only use this one here. Okay, so we write the constraint without equality. Yeah, like that. Now, finally, we are going to find delta Lagrange over delta x. So we find the main part's derivative with respect to x, it is y. So, and derivative of the second part, here y and 10 is constant, so we have only here, so minus x, sorry, it's with respect to x, so minus lambda, it is 0. And here we have y is equal to lambda, this is first one. And second, delta Lagrange over delta y. Again, we look here and we find the derivative of xy with respect to y, it is x. And take the derivative of the second part with respect to y, and it is, you see, y is 1, x is 0, and minus 10 is 0. So multiplied by minus lambda, it is again minus lambda is equal to 0, and x is equal to lambda also. So I said that this is an easy question. So we find easy functions. Y is equal to lambda, x is equal to lambda. And finally, let's find delta Lagrange over delta lambda. And this is the constraint, as I said before, x plus y minus 10 is equal to 0. So we have x plus y is equal to 10 is the third one. So by using 1 and 2, you see that we find x is equal to y, and by putting this one on the third equation, so x plus x is equal to 10. It is 2x is equal to 10 and x is equal to 5. So we know that x is equal to y. x is equal to y. So y is equal to also 5. So finally, we have x is 5 and then y is 5 amounts are the optimum values. Optimum values. So if we put these values on the uxa function, what I mean this one, Let's use again uxa function. It is x multiplied by y. And if you put 5 and 5, that is, of course, using by this constraint is equal to 10, we have 5, 5. And finally, 5 multiplied by 5 is 25. So this is the maximum value for uxy. Let's think another thing, such as 7, 3. You see, 7 multiplied by 3 is 21, not maximum. Such as 4, 6, that is 24, not maximum. Maybe 9, 1, it's 9, not maximum. So 5, 5 is the maximum value, and we find these values, optimum values, by using Lagrange function. Okay, it's important. And I have one more question, and I'm going to write it, but solve it in the lecture, online lecture. You may try this one when we come to the online lecture, of course. We have 7 or 8 days. And uxy, this is a bit harder, maybe, as a previous question, is equal to 80x minus 2x squared minus xy 3y squared plus 100y is the main function, and the constraint function is x plus y is equal to 12. So question is, find optimal x and y to make uxy maximum. And also find the maximum value for uxy with the optimum values x and y. Yeah, this is a good question. Please try this one for the online lecture, and I will also ask to you this one. Okay, see you for the other day. Bye bye.